Welcome back from spring break. I hope everyone is healthy at home right now. Bear with me, and I promise to be patient with you guys as we work on getting this class online so that we can all stay at home and safe and healthy. Today we will jump into the new material that we need to cover, beginning with sampling. I'll be posting recordings of all of the lectures online. I will also be trying to find YouTube tutorials for things that I won't be able to show you in person in class, as well as providing some written documentation about study guides or different ways to think about some of the topics to maybe help you guys pick up on some of the topics that can be more challenging. And unfortunately, the most challenging topics show up at the end of this class, which now we have to do online, but we will do the best that we can and get through it, okay? Okay, so a refresher about where we left off in the course. All right, so we had specified our research problem. We decided that we were going to study the use and possible abuse of ADHD medications by students at the University of Mississippi. You guys did secondary research to write this background research paper on the topic, and we came up with a list of research objectives. And then you guys wrote surveys to try to get data to answer those research objectives. Now, one thing that I want to say about the survey, and I'll send this information out in an email as well, the surveys are almost finished being graded. A lot of stuff has happened, and so that kind of got pushed to the back burner. When I do finish grading them, I will scan the pages of all of the assignments and email those scanned pages to the group members in each group so that you not only get your grade, but you can also see where I marked things up and comments on the survey and things like that. The final survey is written, and I will be sending you guys a link. The way that this final survey is going to work in terms of getting a grade, I will send you a link to the Qualtrics survey. You will send that link then to your friends, roommates, people you work with, other people that you know at the University of Mississippi, and ask them to complete the survey. The very last question in the survey is going to ask them to report your name, all right? So not their name, not the name of the person taking the survey, but it's going to ask them which student from Marketing 525 recruited them to participate in this survey, and they're going to type in your first name and your last name, all right? So you might want to warn the people that you're sending the survey to that that question is coming so that they can be prepared to type your name in. Why are they doing this? The reason why they're typing your name in is because I'm going to look in the data set and see how many times each of your friends have taken the survey and reported your name. All right, everyone in class is required to get 10 people to complete the survey. And if you can get 10 people to complete the survey, then you will get a 5-point quiz grade. All right, so that's how this completion is going to get graded. That is not due for a while. All right, so the data set itself is not due until April 7th. And I know that we're, because we had another week of spring break, this now means that there's only about 2.5 weeks to complete that. All right, but it's just 10 people. All right, so this is not an impossible task. And every week I will post updates on Blackboard showing you not your grade for this assignment, but a count. How many people have taken the survey and listed your name, all right, as the person who recruited them. And once you get to 10, you don't have to ask people anymore to take the survey. But until you get to 10, you should continue sending the survey out to people. All right, and so I will send you guys an email with that link to the survey and reiterating all of the information that I just gave you about that. But that's your next assignment, all right, that you should be concerned about. Okay, so we specified the problem. We designated our research objectives, developed an appropriate research design. All right, so we decided that we needed descriptive research, and specifically that we were going to use a survey to collect this information. Then we crafted the data collection instrument. It's just a big word that means survey. All right, and so now the next step in the research process, right? So not for our class project exactly, but if you were doing this research process out in the real world, the next step would be to create the sampling plan. All right, and so that's what this entire set of slides is about how we sample. And what we talk about, what we're concerned about when we talk about sampling plans is answering several questions. First, who are we going to survey? All right, so who are the people that we want information from? All right, who are the people that we're interested in having complete our survey? How are we going to select them? All right, because we're not going to ask everybody. All right, similar to if you think about our class project, there are thousands of students at the University of Mississippi, and we're not going to ask every single one of them to answer our survey. So how are we going to choose some subset of people to answer the survey? And finally, how many people do we need? All right, so what is the magic number that we're looking for of collected responses that's going to be enough, all right, to make us think that we got good, reliable data that we can then analyze, all right, to find answers to our research objectives. Okay, so what is sampling? Sampling as a term that needs to be defined is the process of obtaining information from a subset of a larger group. All right, and we're going to get into some more specific definitional terms in a few slides. But what this means is there's some large group of people that we're interested in. All right, we would like ideally to get answers from all of them. All right, as an example, in our class project, we're interested in knowing what students at Ole Miss do. All right, so this is the larger group that we're talking about, students at Ole Miss. And sampling refers to talking to some subset of that larger population, and then we're going to take the answers that the people in our sample give us, all right, so the subset of students who complete your survey, we're going to take their answers, and then using the statistics that we'll get to later, we're going to use their information to generalize to the entire population, all right, so we're going to say, based on what I learned from this subset of people, here's what I think is true of the larger population, all right, or here's my best, most educated guess, all right, and guess sounds a little unscientific, all right, so the statistics put a science on it, all right, but we're using this information to generalize to the entire population, all right, and the interesting thing here is that most of the time people who are not educated about sampling, who haven't taken courses in research methods, overestimate how many people are needed to really get good information about a larger population. The kind of cool thing, all right, for somebody who does research, because it's very difficult to get very large samples of people, is that as long as the sample is well drawn, and we'll talk about what that well drawn part means in a minute, the study results should be fairly accurate when they get generalized to the population. All right, so as an example, most political polls that do really important things like try to predict who's going to win elections, all right, and things like that, they only sample 1,000 people, all right, out of the millions, tens of millions of people who live in the United States. They sample only 1,000 people, all right, and historically they're very accurate. Save 2016. All right, weird stuff happened in 2016 with polling, but prior to that, these political polls were always very accurate at predicting who was going to win elections based only on information from 1,000 Americans, which is a tiny, tiny fraction of all of the people in the population. But for numerical reasons that we'll talk about later, you only need, all right, this 1,000 is a perfectly adequate sample size, even if your population is very, very large. All right, and so the key thing is sample size is important. 1,000 is an important number for a reason that we'll see at the end of this slideshow, but the biggest, most important thing is that the sample that you draw needs to be representative. All right, it needs to be representative of the population that that sample was drawn from. And what this means is that the people who are in your sample, all right, the people in the subset of the population who actually answer your survey or participate in your experiment, they need to look like the larger population, right? And we talked about this when we talked about test markets, and we said we had to identify cities that were average, right, where the people in the city looked like the larger US population. It's the same thing here. If you're drawing a sample from the population, you want the people in that sample to look like, right, I'm using air quotes here, look like the larger population in the sense that their average demographics, their average socioeconomics, economics, etc., are mirroring that of the larger population. All right, so you're getting this tiny version of the larger population. It's not just all women, it's not just all young people, all right, it's a group in your sample that looks like the larger population. Okay, so on the last slide, I said that ideally we would get information from everyone in the population. All right, so if we want to know what are Ole Miss students doing with respect to using ADHD medications, then why don't we just ask every Ole Miss student to take our survey and tell us what they're doing with respect to using ADHD medications? Well, the problem is that it is really time consuming and really expensive to try to contact everyone in a population. All right, and we talked about this when we were first learning about error, and we said, even if we had a simple question we were trying to get an answer to, like what is the average height of men at Ole Miss, we said that our first step would be we would have to find every guy at Ole Miss. And we talked about all of the things that would make that difficult, all right, that some members of the population would be abroad, all right, or they wouldn't live in Oxford. And even if they did all live in Oxford, it would be very difficult to incentivize all of them to come to a single building to take this survey or to be measured, all right, and so it would be hard to get every single person in the population. And in fact, it's hard for everyone, all right, to try to find everyone in a population, and that's why almost everyone relies on sampling. All right, even the US government tries to get information from every member of the population through the census. All right, they hire an army of workers to go door to door to get this information from people who don't voluntarily return the census, and they're still incapable of getting every member of the population, and so they rely on a sample. All right, so this isn't, it's not giving up or taking the easy way, it's just what's done in research because it's impossible to get a population. All right, so we accept that we're going to have a sample of people. All right, but despite the fact that we're only going to talk to a subset of the population, we still want to estimate what's true for the entire population. All right, so we're going to get some subset of Ole Miss students to answer our survey about ADHD medication use, but we don't just care about what that subset of people is doing, we care about what the entire population is doing, even if we can't talk to all of them. So what we do is we take information that we get from the sample, and then we use that information to make inferences about the entire population. All right, so we're having a preview here of the statistics that we're going to get to later. You guys are going to have to bear with me because I'm going to try to write on this slide, but I don't have a stylus, so I'm going to have to do it with my mouse, and it's going to get ugly. All right, so the population has certain characteristics, all right, that we're interested in, and these characteristics in statistics language are referred to as population parameters. All right, and so when we say that it has certain characteristics, those characteristics could be anything. All right, so with respect to our research objectives, a characteristic that we might be interested in knowing is what proportion of the population has ever taken ADHD medication without a prescription. All right, or the characteristic might be what proportion of Ole Miss students have, a medical diagnosis of attention deficit disorder. All right, so there's just something about the population that we're interested in knowing, and if we could know that thing at the population level, all right, so if we had perfect information from the population so that we could say, here is a number that represents this quantity existing at the population, that would be referred to as a parameter. When we collect a sample, right, we collect information from the sample, and this information that we collect from the sample is referred to as a sample statistic. All right, and this is where statistics as a word sort of is coming from here. All right, so if we conducted a census, we got every single member of the population, we measured something without error, all right, from those people in the population, every single person told the exact truth, then we would be able to calculate the population parameter, all right, the exact percentage of people who have done something. We can't do that. All right, so we can't get a census. We're not going to talk to everyone in the population. We also know that some people are going to lie, some people are going to misunderstand questions, some people are going to forget and estimate a quantity instead of telling the exact truth. All right, and so what happens is we send out our survey to some subset of people. There's measurement error, all right, when we collect this data. And the result that we get from that surveying is referred to as a statistic. Down the line, all right, a couple of lectures from now, we're going to talk about how we use those sample statistics to estimate what's true for the population. All right, and so we're going to talk repeatedly about this, this equation down here at the bottom of the slide, this expression where there is something about the population that we're interested in knowing. All right, don't laugh to yourself at my writing. The population, there's something about the population that we want to know, and we're going to estimate that quantity. All right, for example, what proportion of students at Ole Miss have tried ADHD medications? All right, there's something about the population we want to estimate, and we're going to estimate that population parameter by looking at the statistics that we get from the sample. All right, so the answer that we learn from our sample, the answers that we get on our survey, We're going to combine that information that we get from our survey with some estimate of how much error there was in our measurement. And we're going to put those two pieces of information together. What did we learn from the sample and how much error was there in our measurement? We're going to put those two pieces together to estimate what do I think is true of the population. All right, and that error is going to come from systematic errors, which are those ways that we talked about, the biases that lead people to give inaccurate answers to survey questions, as well as that error that arises simply from sampling. All right, because we're not talking to everybody, we know that the answer we find in our sample is not exactly equal to the population answer, because even one additional answer, all right, from one missing member of the population would have changed, all right, our calculation from what we found on our survey. And so we know we're always going to have this sampling error. All right, so even if we assume, it would be a false assumption, but even if we assume that no one lies, so there's no systematic error, everyone's providing the exact truth, as long as we draw a sample, that sampling error is going to exist. All right, the only way to get rid of sampling error is through conducting a census, getting every single member of the population to take the survey. So as long as we're sampling, there's going to be some sampling error. And so later we're going to say what we found in our sample plus or minus some error is our best estimate of what's true of the population. All right, so now that we've discussed broadly why we need to sample, let's talk about how we actually do it. All right, so the textbook, as usual, likes its list of steps, all right, and especially at a time like this, I'm going to try to be as consistent with the textbook as possible. All right, so we will start with step 1, all right, which is defining the population of interest. All right, I've used this word population several times already in these slides, but defined from the textbook, the population consists of all cases, all right, which is just a research word that means people, that meet designated specifications for membership in the group. All right, and this is a kind of vague definition, but what this means is who is qualified to answer your survey. All right, and so when we talk about the population of interest, this does not necessarily mean the entire population, all right, so the entire world population or the entire US population. It means who is the group of people that's relevant to your research question, all right? And so this could be fairly broad, all right? Like we talked about national brands when they're doing test markets, they could be trying to sell to all Americans. So the entire US population could be your population of interest, all right? But it could also be, if you're a cigarette manufacturer, people over 18, all right? If you are a person who markets a product specifically to women, then maybe you're only interested in women's opinions in your survey. Or maybe you want to talk only to people with a college education or people who have used your product in the last 30 days. In our case, in our class project, our population of interest is current students at the University of Mississippi. All right, so it's not all students, it's not all people, all right, it's just current registered Ole Miss students. That is our population of interest. Some things to consider when you're defining this population, although, realistically, your population gets defined based on your research question, but the simpler the definition of this population of interest, the easier and cheaper it is to find a sample, all right? So the more people that there are in your population and the easier it is to define membership in that population, the easier it's going to be to find people. All right, so it's going to be much easier to find people over 18 or women, all right, to participate in a survey than it would be to find women who are over the age of 18 and have a college education and have used your product in the last 30 days. All right, that's a lot of qualifiers that someone would have to meet in order to be eligible to participate in your survey. All right, so the simpler your definition of population, the easier it is to find people from that population to then take your survey. All right, so the flip side of that is the more complex your definition, the more qualifiers you place on who's qualified to answer your survey, who's a member of that population you're interested in, then the more difficult and more expensive it's going to be to find a sample because it's just harder to identify members of that population at the outset, all right, to then ask them to participate in your survey. So once you have identified the population from which you're going to draw your sample, the next step is to choose a data collection method. Now, honestly, this isn't really a step because you've already chosen the data collection method. All right, so we already know that we're going to have a survey and that survey is going to be online. And so while this is presented as a step, it's really a point where some considerations need to be made. All right, so the data collection method that at this point in the research process you've probably already chosen. All right, you already know if you're going to do paper surveys or email surveys or face-to-face surveys. This choice that you've already made can contribute unique considerations to your sampling decision making. Right, so we've already talked about how mail surveys, right, where you print off a survey, put it in an envelope, mail it to people's houses, are more likely to suffer from non-response bias. To take us back before the midterm, recall that non-response bias is a type of error that stems from people choosing not to participate in surveys. All right, and so we said that this is higher in mail surveys because it's very easy to just throw away a survey that comes to you in the mail without opening it. There's no person there, to hold you accountable to actually complete that survey. And so because mail surveys suffer from non-response bias, later in this set of slides when we talk about how large your sample needs to be, the fact that you know that a large proportion of people will not return that survey at the outset dictates that your initial sampling needs to be higher, all right, to compensate for the fact that a lot of people will choose not to return the survey. And we'll talk about that more in a little bit. Telephone surveys, if you're planning on calling people, then you need to consider the fact that a lot of people exclusively use cell phones. All right, so you should not be using a phone book, for example, to find phone numbers to contact people, because you will miss a large swath of the population that does not have a phone number listed in a phone book, and that a lot of people will screen their calls. All right, and so if they see a phone number that they don't recognize, they just won't answer the phone, and that contributes again to non-response bias. And so you'll have to find more phone numbers at the outset, knowing that a large proportion of those phone numbers will not answer the phone and complete the survey. And internet surveys, again, suffer from non-response bias. All right, we talked about people having multiple email accounts, and if a survey goes to that email, they never see it, and now they're considered non-respondents. But in addition, it can be difficult to get certain kinds of people to answer internet surveys. All right, so you're going to get the very elderly who may not have good internet access or not tech savvy. All right, they might not be looking at email frequently. It's also difficult to get professionals, all right, where their inboxes may be flooded with lots of mail that they consider spam, and so they're just deleting all of those emails and might overlook a survey. If you choose to use what's called a panel, right, remember we discussed this previously, this is where groups of people sign up to be members of a website where they get paid to complete surveys. Those panels may not be representative because of self-selection bias. All right, so these people are choosing to complete surveys in exchange for money, and we might wonder, are certain kinds of people more likely to do this? All right, and so as a result, these panels may be composed of people who are not truly representative of the population. All right, and so if we rely on panels for collecting data online, then we might not get a representative sample. And remember, our overarching goal here is we're trying to get a subset of the population to take our survey such that that subset looks like, all right, or is representative of the larger population. So anything that leads us to get an underrepresentative sample, a non-representative sample, is going to be problematic and counterproductive. All right, it's not going to get us to our goal of collecting data that we can use to make inferences or estimates about what's true of the population. All right, our next step is to identify a sampling frame. All right, and this is the beginning of the actual process of coming up with that list of names that we're going to contact to participate in our survey. All right, and so what a sampling frame is it's a list of all of the people in the population we're interested in. All right, and so once we have this list of names, we're then going to draw names from that list, and the names that we draw are going to be our sample. Sometimes this list actually exists. All right, so if we think about if we wanted to do a poll of registered voters, there is somewhere a list of all of the people who are registered to vote. All right, so that sampling frame exists. We might not have access to it, but it exists. A couple of years ago, the Ole Miss Alumni Association approached our class and asked if we would do our class project on a topic relevant to the Ole Miss Alumni Association. And so we wrote a survey to ask questions of the alumni, and in order to draw a sample, they provided us with a list of all of the Ole Miss alumni in good standing, all right, meaning they had paid their dues in the last year. All right, and so then we did have a sampling frame. We had an actual list of all of the people in the population that we were interested in, and we could take a subset of those names and contact them. Most of the time, though, there's no list of names. All right, so if we were interested in surveying anyone who's used the internet in the last week, all right, maybe like the CIA has this list, but it's certainly not a list that any normal person would have access to. If you are a soft drink manufacturer and you want to survey anyone who's purchased soft drinks in the last month, there's no list of all of those names. All right, and so in those cases, when it's impossible to actually come up with a list of names, the sampling frame, all right, or creating a sampling frame, means that we just need to identify the procedures that we're going to use to produce a representative sample with desired characteristics. All right, so what are we going to do to make sure that the people that we're contacting are appropriate to complete our survey? And in our case, hypothetically, there is a list. So we're interested in talking to students at the University of Mississippi. There is a list of all students that are currently registered at Ole Miss, but the registrar is not going to give it to us. All right, so for us, this sampling frame procedure means that we're going to have these screening questions at the beginning of our survey asking respondents, are you 18 years or older? Are you currently registered as a student at Ole Miss? If they answer yes to both of those questions, then they are in our population of interest, and that means they are qualified to participate in our survey and become a part of our sample. All right, so once we have a list of the names of the people in our population, and I know that I just said that oftentimes there is no actual list, but for the purposes of learning these sampling methods, we're going to pretend that there is an actual list of names that we can draw names from. All right, so once we have that list, the next step is to determine how are we going to choose the specific names from that list that we want to send our survey to. All right, and there are two broad ways that we can do this. All right, we can draw a probability sample and we can draw a non-probability sample. And we're going to look at 3 or 4 specific sampling methods within each of these broad categories. But first I want to talk about the characteristics of the categories themselves so that we can help to separate these in our mind and understand what makes a probability sample what it is and what makes a non-probability sample what it is, regardless of the specific method that gets used within that umbrella term. All right, so we'll start on the probability sampling side because this is the side where it's a little trickier to understand exactly what's happening. All right, so with a probability sample, these are sampling methods in which every element of the population, so each name on the list, has a known non-zero likelihood of selection. All right, and so what those two terms mean, known and non-zero, is that let's imagine that there were 1,000 students at Ole Miss and we had a list of those 1,000 students' names. If we were going to use a probability sampling method, that would mean that there was going to be some element of randomness in our draw, and because of that element of randomness, each person on that list of 1,000 names would have a 1 in 1,000 chance of being drawn. All right, so their probability of being drawn is known, all right, it's 1 in 1,000, and that known probability is non-zero. Every single person on the list has a chance of having their name drawn, and we can calculate that specific chance, all right, that any specific person's name is drawn. All right, and so the results of drawing a sample in this way is that you necessarily end up with a representative sample. All right, and remember, a representative sample is our goal. All right, it's our main thing that we're focused on, making sure that the members of our sample look like the members of the population. With probability sampling methods, you get a representative sample. All right, that's the benefit of doing the additional steps that we'll see in a minute that are necessary to get these probability samples. Let's talk about for a second why you necessarily get a representative sample. Let's imagine, all right, going back to Stat 101, you have an urn, and in that urn there are 10 yellow balls and there are 10 blue triangles. All right, and so our population consists of 50% yellow circles and 50% blue triangles. All right, and you can think of this as male and female if you want to put this into the context of surveying people. All right, so we have this population. Imagine inside this white circle, these are all the people in our population of interest. 50% of them are male, 50% are female. Doesn't matter if the males are the circles or the triangles. Let's imagine that we randomly draw names from this population, all right? And we can think of this as there are 20 names in a hat, we stick our hand in and we draw out a name. And let's imagine that these circled people are the ones who had their names drawn. because of the laws of probability, all right, because each time I put my hand into this hat, I have a 50% chance of drawing a woman's name and a 50% chance of drawing a man's name, all right, or a 50% chance of drawing a circle and a 50% chance of pulling out a triangle. When I stick my hand in repeatedly and pull out circles or triangles, I'm going to end up with a sample, all right, a subset that is going to be roughly 50% circles and 50% triangles. All right, this is the same as if you think about you have a fair coin, all right, one side is heads, one side is tails, and you flip that coin a bunch of times. Once you flip the coin enough times, you're going to end up having flipped roughly 50% heads and roughly 50% tails. All right, this is just probability at work. If half of the population is male and half of the population is female, and I randomly pull names from that population, then the laws of probability dictate that the names that I pull, there's a 50% chance the name I pull is going to be male, and there's a 50% chance the name I pull is going to be female, and as a result, I'm going to end up with this sample, this subset of the population that is comprised of 50% males and 50% females, right? And this is why we necessarily get a representative sample when we do this. In the example that I have up here on the slides, we have only one characteristic that we're looking at, all right, shape or gender, if we want to, say the circles are male and the triangles are female. But this holds true for all of the characteristics that we can think of, all right? So the people in our population are going to vary not only on their gender, but also on their race, their year in school, their GPA, whether or not they have an ADHD diagnosis, whether or not they're Greek, whether or not they're an athlete, whether or not they're an honors student, what their major is, this whole variety of things, all the ways that the students on campus are different. And if we think about roughly a third of students are in Greek organizations. That means that every time I would put my name, or I would put my hand into the pot of students' names, I have a 1/3 chance of drawing a Greek name and a 2/3 chance of drawing a non-Greek name. And that means that once I pull enough names out of the hat, my sample should consist of roughly 1/3 Greek students and roughly 2/3 non-Greek students. All right, and so for all of these various characteristics that we're interested in, this random drawing of names should result in a sample that fairly closely resembles the actual population. All right, we're going to see this in at work in an example at the end of the slides. All right, but this idea of probability, all right, is why these are called probability samples, and it's also what leads us to get representative samples when we use these measures. Because we have these representative samples and because of the probability that's at work, behind the scenes in these kinds of sampling methods, the sampling error can be predicted. All right, and why is this important? Bear with me, I'm going to try to write again on these slides. Remember earlier I said that we are going to make an inference about what's true of the population, all right, POP, the population, and what's true of the population, we're going to estimate that by looking at the answer that we get from our sample, all right, SAM, plus or minus our estimate of error. All right, so we have to have some estimate of how much error there is in our measurement. And when we use a probability sampling method, we can calculate how much error, how much error there was in our measurement. We are not going to talk about mathematically how that error is calculated, and SPSS will do that calculation for us, so we don't even have to worry about it. But just know that when a probability sampling method is used, we can calculate this part of the equation. All right, so once we get the answer from our sample, hopefully you guys can see this little dot swirling around here. When we get the answer from our sample, and now we can calculate how much sampling error we have in our measurement, we can use these two pieces of information to then make an inference, all right, about what we think is true of the population. All right, and so when we collect data using a probability sampling method, we can project, we can project information that we learned from our sample onto the total population. We can say, based on what my sample said, here's what I think is true of the population. Now, obviously, this sounds like what we should do every time, all right? We should always use probability sampling methods so that we can have this outcome, all right, of being able to project to the total population. The problem is there are limits to when we can use probability sampling methods, the biggest limit being we need a good sampling frame to do it. All right, and so because using this kind of sampling method is not always feasible, we have another option. All right, and that other option is to use non-probability sampling methods. The non-probability part here in the title is referring to the fact that with these sampling methods, there is no element of randomness. All right, so people are being chosen for some specific reason, and it's not just because their name got randomly drawn from a hat. All right, they're being chosen for some other reason. All right, so these are samples in which specific elements or people from the population have been selected in a non-random manner. The big benefit here, they cost less. All right, it's less involved to try to collect this kind of sample, and they can be gathered more quickly than a probability sample. All right, so there's cost savings, there's time savings, and we'll see one version of a non-probability sample that tries to create as representative as possible, right, of a sample. So some steps are taken to try to create representativeness in the sample, but because this randomness is not present in the draw, we cannot calculate sampling error. All right, so when we use a non-probability sampling method, there's no element of randomness, and we cannot calculate how much sampling error there was in our measurement, and so we don't have this part of the equation. All right, so we're going to get some information from our sample using a non-probability method, but we don't have the error piece of this equation, and as a result, we cannot make that inference about the population because we're lacking information that we need. All right, so when you collect data using a non-probability sample, you should not use the information from that survey to make inferences about the overall population. In our class project, you guys are going to collect a non-probability sample, and we are going to do this anyway because we have to, all right, for the sake of learning. But out in the real world, that would not be appropriate, all right? And we're actually going to talk about, this is one of these places where as consumers of other people's research, you need to ask yourself, did they collect an appropriate sample? Because the way in which samples are drawn can really drastically affect the results of a study. Okay, within each of these two umbrella categories, probability and non-probability sampling methods, we have a couple of specific ways, all right, in which people are identified to participate in the survey. All right, so we're going to go over those now. We're going to talk about the non-probability sampling methods first because these are the least sort of technical, so they're easier to understand what's happening here. All right, the first kind of non-probability sample that we're going to talk about is what's called a convenience sample. All right, and this is actually the sampling method that you guys are going to use when you collect data for your ADHD survey. With a convenience sample, choosing who is included in the sample is a matter of convenience, all right, as the name suggests. And so what this means is that instead of, as with a probability sampling technique, having a list and then choosing some random way in which to draw names off of that list, with a convenience sample, you just ask the people who are around you to take a survey. All right, and so in your case, as I mentioned at the beginning of these PowerPoint slides, you guys are going to email or post to Facebook or, post to whatever kind of group chat kind of things you guys have working. You're going to post this link and ask people to participate in the survey. The people that you ask to participate in the survey are going to be the people who are convenient to you, right? Your friends, members of your sororities and fraternities, people that you live with, people that you work with, all right? People who are in the same major as you, so you know them, you've seen them in previous classes. These are all convenient to you, all right? There's no extra effort being taken to ensure representativeness here. The result of this, all right, going back to what we talked about on the previous slide about how probability methods, where there's an element of randomness to the draw and how that necessarily results in a representative sample, we can start to see here with these non-probability sampling methods where the problems are, all right, how we're going to end up with a non-representative sample. All right, now if we were in class, I would ask you guys to look around the classroom, look at all the faces of your classmates, think about who's convenient to those people, and then tell me what kinds of students are going to be overrepresented in our sample, meaning they are going to exist in our sample in a higher proportion than they exist in the population. All right, and so we can pause for a second. All right, and you guys think about who do you sit next to in class? Who do you see, all right, from your chair when you're sitting in class? the kinds of people who are going to be overrepresented. All right, and we're going to see this. I mean, we're going to see it happen in our data set. This is going to be confirmed later in the semester. There are going to be too many business majors. All right, you guys are business majors. That means that a lot of the people that you know are business majors, and so a larger share of our sample is going to be a business major than exists in the actual population. All right, there's going to be too many women. All right, the class is more than 50% female, and generally, I don't have like data or research to support this, but my feeling is that women are more inclined in this class setting to take surveys for their friends than men are, and so as a result, we tend to see more women in our sample than there are at the university generally. Our sample is going to be too white. All right, there are way more white students in our research classes than there are students of other races. I don't know if that's because marketing is just a more popular major among white students, or what the reason is, but the result of that is going to be that in our sample we're going to have a smaller proportion of other ethnicities than exist at the broader university population. So there are going to be too few racial minorities and too many white students in our sample. There's also going to be too many Greek students. All right, so the Greek students tend to make up about 1/3 of the student body population, but as we'll see doing some statistics later in the semester, there are going to be a lot of business majors are Greek. So there's a lot of you in class who are Greek students, more than is typical for the broader student population. And our samples generally tend to, skew to about 60 to 65% Greek, which is about twice as many Greek students as exist at the population level. So in all of these ways, this convenient sampling method of having students in class ask people like them, all right, their friends, to take this survey, we're going to end up with a sample that is not representative of the population. All right, and it's for that reason that technically we should not be using the answers from our survey to make a generalization to the entire student body population, but we're going to do it anyway to help you guys learn statistics. All right, but this is how these convenient samples result in non-representative samples. All right, why although it's easy to conduct a convenient sample, it's cheap to conduct a convenient sample, it has problems. All right, and so even if you take a step to say, well, I'm not just going to ask my friends. I'm going to go, imagine that it's not the way it is now, but you say, I'm going to go stand in front of Walmart and I'm going to ask people as they're coming into Walmart to answer the survey. And you say, well, if I do that, then I'm getting random people to take the survey. That's not random, all right, the way that we talk about it statistically. This colloquial use of, oh, that's so random, that's not what it means, all right, in a probabilistic sort of sense. If you go and you stand in front of Walmart and you ask people who are coming into Walmart to take your survey, yes, you are likely to get a more diverse sample than if you just ask your friends, but who is included in the sample remains a matter of convenience. All right, so every element of the population will not have a known and non-zero chance of being selected. Anyone who was not planning on going to Walmart that day has a 0% chance of being selected in your sample, and we cannot calculate the probability that each student at Ole Miss gets drawn into your sample. All right, so we're still going to end up with this non-representative sample where everyone doesn't have a chance of being drawn, and we can't calculate the sampling error. All right, so convenient samples are cheap and easy, all right, but they have problems. Another kind of non-probability sampling method is what is called a judgment sample. All right, and with a judgment sample, people are handpicked from the population because they're expected to serve the research purpose, right? They're expected to have information that we want. Now, this judgment sample can get combined, with the convenient sampling procedure if, for example, you think to yourself, who am I going to send this survey link to? You think, oh, I know these 3 specific friends that I know take ADHD medication without a prescription. And so I'm going to send the survey to them because they're the kind of people that we're interested in talking to. That's a judgment sample. All right, and again, certain people have a known, they do not have a known and non-zero likelihood of being selected, because with a judgment sample, some people have much higher odds of being drawn and other people have much lower odds of being drawn, or 0 odds of being drawn. Judgment samples are sometimes used in conjunction with something that's referred to as snowball sampling. This is where you have some group of people, right, that are perhaps it's difficult to contact that group of people. Right? And so as an example, when I was in grad school, as a job, to make money, I worked on this project at the local hospital where we were doing this research project to try to identify risk factors for getting kidney cancer. And so we had to find people who had kidney cancer to give our survey to so that we could ask them about all of these life experiences they may have had that contributed to their eventually getting kidney cancer. And it's not like there's some list somewhere of a bunch of people who have kidney cancer. So once we identified doctors who treated patients that had kidney cancer, we would ask those doctors to identify additional patients who might be willing to participate in our survey. All right, and so this snowball, where this snowball term is coming from, is you identify one person. All right, let's imagine this scribble that I've just drawn is one person who meets our sampling criteria. All right, in this case, it's a person who has kidney cancer. They're willing to take our survey. And at the end of the survey, we ask that person to identify 2 other people who would be willing to take the survey. All right, so we get these other 2 people to take the survey. And now once they've completed it, we ask them to identify 2 people. All right, and so in this way, by continually asking survey participants to identify new survey participants, we can grow our sample exponentially, all right, like a snowball rolling downhill, gathering more snow. We can collect more participants in our sample, and this is especially useful in times where it's difficult to identify members of the population, or it's difficult to contact members of the population. All you have to do is find this one initial person, and then you use that one initial person to help you identify new people who are relevant to your research study. All right, let's get rid of this. All right. As I mentioned on the previous slide, non-probability samples can try to create representative samples. It's not perfect, all right, but they can try to do a better job of getting a representative sample, and a quota sampling procedure is one way in which you can use a non-probability sampling method but try to be more representative. The way this works: let's say you identify some aspect of the population, for example, gender, and you say, it's really important to me that my sample perfectly mirrors the population on this one criterion. All right, so you say, I have men and women in my population, and let's say that you know that the population is 50% male and 50% female. So you want to collect a sample of 100 people, and you want that sample to perfectly mirror the population on gender. That means that you would need 50 men, sorry for this terrible mouse writing, and you need 50 women. All right, so you establish these quotas. I need 50 men to take my survey and 50 women to take my survey. And if I accomplish that, then my sample will perfectly mirror the population on this one criterion, all right, that I think is especially important. All right, and you can have more, although the more criterion you have, the harder it is to establish these quotas. So then once you've established these quotas, you would typically use a convenient sampling method. Let's say you go to Walmart, the first 50 men who walk by, you ask them to take the survey, and then once you've collected your 50 men, you say, okay, I'm done with the men, now I'm going to collect 50 surveys from women. All right, the problem with this, the reason why it's not perfectly representative, is because while you have perfectly mirrored the population on this one criterion, all right, gender, it is not going to be representative of the population on all of the other things that might matter, all right, like ethnicity, income, education level, etc. All right, so if you think about the kinds of people who shop at different stores, if you go and do this in front of one store, the population, the population of that store might not match the overall population. And so while you've done a good job of getting a sample that mirrors the population on this one criterion, it's not going to be representative on the others. All right, so it's trying to be better, but it's still not perfect, all right, because it is a non-probability sample. People are chosen for a specific reason, all right? They're either in the right place at the right time, they have information that we specifically want to get from them, or they match one criterion that we're interested in. But because they're picked for a specific reason and they're not picked randomly, the result is that we end up with a non-representative sample. All right, and remember, our goal here is to get a representative sample. And the only way we can do that perfectly is to use a probability sampling method, which we're going to talk about on the next slide. Okay, the probability samples. Remember, the key thing here as we go through these different sampling methods is that in each one there's an element of randomness. All right, at some point there's going to be a random draw of names, and where that randomness comes in the procedure is going to change across these different methods that we talk about, but it's there. All right, that's the key thing to look at when distinguishing between these. All right, the sort of gold standard for sampling is what's called a simple random sample. With a simple random sample, each unit in the population has a known and equal chance of being selected for the sample. All right, and this is akin to drawing names out of the hat. All right, the thing here, remember, sorry, I'm rambling a lot as I record these slides, but several slides back now, we said that these probability sampling methods require having an actual list of names. All right, so a simple random sample is akin to taking that list of names, cutting each person's name onto an individual square, putting them into a hat, and randomly drawing names one at a time from that hat. All right, and so every name in the hat has a known and equal chance of being selected for the sample. Their chance is 1 in however many people are in the hat. Okay, this is the best way, all right, to draw a sample. It ensures a perfectly representative sample. The way that researchers try to accomplish this, or one way they try to accomplish it, even in the absence of a list of names, is by something called random digit dialing. What random digit dialing is you have a program on your phone or this machine that gets attached to a physical, non-cell phone, a rotary, not rotary, all right, whatever they're called, an analog kind of phone, old phones. And what the machine does is that it randomly generates a 7-digit string of numbers, and then it calls that phone number. All right, and so this is how even, people are in this uproar about putting their phone numbers on do not call lists. This is how people get called even if they are on do not call lists, because this machine just randomly dials 7 numbers. Now, of course, sometimes it gets fax machines or businesses or numbers that are out of service, but if you have a phone number, it is possible that this random digit machine is going to generate your phone number, all right? And because almost everyone in the United States has a telephone, all right, either a cell phone or a phone in their house, it is possible to reach almost every person in the US population in this way, all right? And so by random digit dialing, it is the closest that researchers can get to collecting this kind of simple random sample. And when you read polls online, these political polls, they report their sampling procedures. They will often report that they used random digit dialing techniques. That's what they're doing. All right, they're randomly dialing 7-digit strings of numbers, 10, I guess, once you include the area code. These 10-digit strings of numbers to contact people living all over the United States to ask them to participate in surveys. All right, a systematic sample. This one's a little weird. Bear with me. With a systematic sample, the time that you would do this is if you only have a printed out copy of the sampling frame. All right, so there's a printed out copy of the list of names of people in your population. So you don't have an online database or anything like that. The problem with having only that printed out list of names is that to randomly draw names, you would have to, cut them all out and put them in a hat. What is more often done is you ask a random number generator to randomly generate a number between 1 and the total number of people on the list, and then you would have the database pull up the people that were that far down the list. So if the random number generator pulls up 234, then the database will tell you person 234 on the list. If you only have a printed copy of names, you have to count down to the 234th person on the list and then circle that name and then ask the random number generator for a new number and then count down to that name on the list. And that's going to take forever. All right, so with a systematic sample, what you do is, let's say that you are going to sample 1/10 of the names on a list. That 10 becomes your unit K. All right, so if you have, let me get my little pen thing back out here. If you have 1,000 people, ooh, that looks bad, in the population, and you want a sample of 100 people, then K would be equal to 1,000 divided by 100, which is equal to 10. And what you would do is you would have a list of everyone in your population. So you would have this sampling frame, a list of all the names of people in the population. And what you would do is you would randomly generate a number between 1 and 10. So you'd have a computer spit out a random number between 1 and 10. And let's say that number was 6. So you would circle the 6th person on the list, and then you would select every kth unit after that. So you would select 6, and then 10 after 6 would be 16, and 10 after 16 would be 26, and 36, ooh, this writing's getting bad, etc. All right, until you got 100 names. All right, so this feels like we're randomly drawing one name and then non-randomly drawing the next 99. But what's happening with this systematic sampling is instead of drawing 100 names one at a time, you are randomly drawing 100 names all at once. All right, so before this first number gets generated, everyone on the list has a 1 in 1,000 chance of being selected. But at the moment that this first number is generated, all right, and remember it's generated randomly, so there's the random part in this probability sampling method. At the moment that this number gets drawn, you have effectively drawn 100 names at once, all right, because that 6 determines that also persons 16, 26, 36, 46, etc. are going to be selected from this list. All right, and the reason why this is helpful is because it's much easier to just count 10 and circle, count 10 and circle, count 10 and circle, than it is to look up the 16th person, then the 254th person, then the 998th person, etc. All right, so it's just trying to make it a little easier to pick names off of a list when you only have a printed list available. This technique is, it's somewhat less often used, all right, because it's not so common that you only have access to a print copy of the sampling frame, and that's when this really comes in handy. All right, another kind of probability sampling method is what's called a stratified sample. All right, and this is a probability sampling method, so there's going to be an element of randomness here, but first we divide the population into mutually exclusive and exhaustive subsets. All right, remember we've heard these terms before, mutually exclusive and exhaustive. What it means is that we're going to create groups and put the names on our list into these groups in such a way that every name goes into one and only one group. All right, and so as an example, because it's the easiest, we might take gender. All right, so we might imagine we have a list of names of students. We're going to divide all of those names into a list of men and a list of women. All right, so we've now created 2 sampling frames. All right, a list of all the male students at Ole Miss, a list of all the female students at Ole Miss. And once we do that, we take a simple random sample of names from each of those lists. All right, so let's say we want a sample of 100 people, and we know that the student body population is 50% male and 50% female. Then we would randomly draw 50 names from the men's list, and we would randomly draw 50 names from the women's list, and we would end up with a final sample of 100. This looks like the quota sample. All right, remember we said with a quota sample, we say if the population is 50% male and 50% female, then we're going to set up a quota. I want 50 men and I want 50 women. The key difference with a quota sampling method, once we set up that quota, we would go somewhere students are. For example, we could stand in front of the library, and the first 50 men who walk by, we ask them to take the survey. The first 50 women who walk by, we ask them to take the survey. That is not a random draw of names. That's a convenience sample, all right? Because people have to walk by us to be included in the sample, and anyone who spends their time on a part of campus that is not near the library does not have a chance of being drawn into the population. With a probability sampling, all right, a stratified sampling method, we set up these quotas, all right? We set up strata. Strata just means a category. So we have a category of men, a category of women. We know we need 50 men and 50 women. And once we set up those quotas, we then take a simple random sample, all right, from each of these subsets, from the subset of men and the subset of women. The reason why we're doing this is we're making sure that our final sample is perfectly representative of the population on this one criterion, but because we're taking a simple random sample, it's also going to be reasonably representative on all of the other criteria, all right, like race, education level, major, Greek status, etc. All right, so we're being perfectly representative on one thing, but because we're drawing a random sample of names from these two lists, we're also reasonably representative on all of the other criteria. All right, so here's the steps. Identify important demographic or classification factors, determine what proportions of the population fall into these categories. So we imagined 50% male and 50% female, and then select simple random samples from each stratum. All right, so from the stratum of men and the stratum of women. This is somewhat less common in marketing research because it's hard to identify a specific criterion of consumers that you would want to be perfectly representative on. All right, so in most cases, being reasonably representative, being pretty close to mirroring the population is good enough. All right, we don't have to make sure that we're perfectly mirroring the population. It's a little bit more popular in political polling or media audience research, where you might want to make sure that you are perfectly mirroring the population on, for example, political affiliation. Or with media audience research, you might want to make sure that you are perfectly mirroring the population on categories like 18 to 25-year-old males, all right, or 26 to 34-year-old males, are these categories that they use when they do advertising sales. All right, so in some arenas, this kind of sampling method is more important. It's somewhat less commonly used in marketing research. All right, the last kind of probability sampling method that we're going to talk about is something called cluster sampling. All right, with cluster sampling, the parent population is again divided into mutually exclusive and exhaustive subsets, but unlike the stratified sampling method, where we're dividing people into what are called homogeneous groups, so everyone in the group is like each other, all right, so we had groups of all men and groups of all women. With cluster samples, each cluster should be as heterogeneous as the entire population. All right, and so these squares down here, let's imagine that each of these squares is a classroom. All right, and dividing people into clusters in this way would probably work in like a high school setting. If people are randomly assigned to a homeroom classroom, then each homeroom classroom should be, roughly as diverse as the entire school population is. This kind of this kind of division would not work at the university setting, as if we think about if this classroom is a marketing classroom, and this classroom is an engineering classroom, and this classroom is a ceramics classroom, then we might expect a lot of differences between the kinds of students that are in these classrooms. All right, so for example, in the marketing classroom, we might expect more women. In the engineering classroom, we might expect more men. We might also expect more racial diversity than we would expect in either the marketing or the ceramics classrooms. All right, and so the key here is that in order to do cluster sampling, you need to have you need to be able to divide your population into clusters where each cluster is as heterogeneous, all right, or as diverse as the entire population is. Now, once you have divided the population into these clusters, you would then take a sample, not of individuals within the cluster, but you would sample entire clusters. All right, so you might say this classroom, and this classroom, and this classroom, and this classroom, and this classroom. We're going to go to each of those classrooms and we're going to ask every student inside the classroom to take our survey. What's the benefit of doing this? If we used a simple random sampling technique, then we could end up drawing names of students in every single one of these classrooms. And that means that we're going to spend a lot of time traveling from classroom to classroom to find every single student on the list that we have drawn their names. And we have to go to every single classroom to find them and ask them to take a survey. With cluster sampling, we're saving some time. We're making this process a little easier on ourselves because instead of going door to door to every single classroom to ask a small handful of students, we would go to a limited number of classrooms but ask every student in the classroom to take the survey. All right, and so there's still an element of randomness, all right, because there's a random draw of clusters. You would put the classroom numbers into a hat and draw classroom numbers out of that hat, and now every student who's in that classroom is going to complete the survey, and you will still get a representative sample as long as each of those clusters is as diverse as the entire population. All right, and so this method, this way of getting a representative sample, really does rest on this assumption that each cluster that you have created is as heterogeneous as the entire population. If it's not, if you don't have a way to cluster people this way, then you shouldn't use this kind of sampling technique. Okay, how's everybody doing? I know that this listening to lectures online is foreign, all right, to a lot of us. There's not a lot of opportunity so far in your education at Ole Miss to have taken courses online, so I know this is challenging. It's challenging for me to sit here and try to talk to my computer screen, and I know that it's challenging for you guys to be listening to my voice for so long in front of the computer screen. If you have not taken a break, I would suggest hitting pause and taking a break now. If we were in the classroom, this is about where we would typically end, all right, with these slides, and we would wait until the following day of class to continue discussing sampling. All right, so if you haven't taken a break yet, now's a good time to take a break. All right, just come back to the slides later, come back to the slides tomorrow. All right, come back whenever you're feeling ready to jump into the next part. I will warn you, there's some math, all right? So be ready to do some math. If you have not been taking notes to this point, totally fine. I don't care if you take notes. This is a spot where you might want to take some notes, or at least try to do the math along with me. All right, normally I would be doing this on the board. I have to figure out how I'm going to do this in slides. But I think that doing the math by hand will help understand what's going on here. Okay, so take a break, and then come back. Are you back? Okay, we're going to talk about how many people need to be in our sample. All right, so far in this set of slides, we've talked about what a sample is and how we draw those names, all right, different techniques using probability and non-probability sampling methods to get members from a population to decide on who's going to actually take our survey, who's going to be in this subset or our sample. The next thing that we have to answer is, how many people do I need? All right, what's my sample size going to be? When we talk about how big our sample needs to be, there are three basic factors to consider, and these three basic factors hold regardless of the size of your population, the question that you're studying, all right? They hold regardless of anything, all right? They are the three basic factors that people always consider. First, how much variation exists in the parameter that you're trying to study in the population. All right, so remember we said that a population parameter is something that can be measured in the population that we're interested in. And when we talk about variation in that parameter, what I mean here is how many different kinds of answers do you expect to get? All right, so if you are asking people a yes/no question, there's not going to be that much variation because people have to answer either yes or no. Right? But if you're asking people to report a number of times that they've done something, then you could expect answers between 0 and infinity, all right? Whatever the ceiling is on how many times someone could have done something or how many of something someone could own. All right, so what's being considered here is, what's the range of possible answers that you expect to get to a question? Is it a big range? Are there lots of possible answers that you could see? Or are there very few possible answers that you could see? All right, the more variation you expect, the more different kinds of answers you expect to get, the larger your sample needs to be. And this is a very simple, if you expect to get lots of answers, then you need to talk to more people so that you can get that variety of responses represented in your sample. All right, so if there's 100 different possible answers that you could get, but you only talk to 10 people, then you're not measuring the true variety of answers that actually exist in the population. However, at its extreme, if, let's say, going back to this example of studying the heights of men at Ole Miss, let's say that because of, some biological disaster, all of the men at Ole Miss are exactly the same height. All right, so men can now grow to just one height. but we don't know what that height is. So we know there's no variation. Every man that we talk to is going to give us the exact same answer, all right? But we don't know what that answer is. If we're trying to learn that height that men are, and we expect absolutely no variation, all right, so I'm not even going to try to draw the Greek symbol with my mouse. If we expect absolutely no variation, all right, so variation equals 0, then we only need to talk to one man to find out how tall all the men are. Because if all of the men are exactly the same height, then talking to this one guy gives us all the information that we need. But, as is actual reality, men can be all kinds of different heights, all right? And so we can see lots of variation in the heights of men on campus. And so if variation is a larger number, then we also need a larger sample size, okay? So the first thing that we're considering is how many different kinds of answers are we expecting to see? If we're expecting to see lots of different answers, then we need a larger sample size. Second consideration, how precise does our estimate need to be? All right, so how much error are we willing to accept? As our sample size increases, our error is going to decrease. All right, and the ultimate example of this is when our sample size is equal to the population size. All right, so when we've conducted a census and our sample is every single person in the population, then our error is 0. All right, if you conduct a census, you have absolutely no sampling error. All right, and so there's this question of how much error we're willing to tolerate. When we say how precise does the estimate need to be, what this is referring to is this expression that we wrote, that our population is equal to what we learned in the sample plus or minus some error. Whoa. All right, and this estimate of our population, the precision of that estimate depends on how much error we have. All right, so if we want a really precise answer, we want what we find in our sample to be very close to what is true for the population, then we need to have very little error, and the way to get very little error is to get a larger sample size. All right, so if you want to be more precise, you also need a larger sample size. All right, let me erase some of this. You can see. Finally, last consideration, what degree of confidence do you want in your estimation? All right, and this is going back to, hopefully you remember from your first stats class, and we're going to talk about them on the next couple of slides. You can say I'm 95% confident, I'm 99% confident, etc. When we take these pieces of information to draw an inference about the population, we make that inference at different levels of confidence. So you can say you're 95% confidence in this inference, you're 99% confident in this inference. The more confident that you want to be, all right, the more confident you want to be, the larger your sample size needs to be. All right, so if you want to be 99% confident, you're going to need a larger sample size than if you're willing to be 68% confident. All right, so more variation, higher sample. More precise, higher sample size. More confident, higher sample size. And importantly, as I mentioned at the outset of this slide, these factors hold regardless of population size. All right, and I can't emphasize this enough. It does not matter if your population has 10 people or 10 million people. If variance, all right, this is this little Greek symbol I refrained from drawing earlier. If there is no variance in your population and you expect every single person in the population to give exactly the same answer, then you only need to talk to one of them. And it does not matter if the population has 10 or 10 million people. If they are all going to give the exact same answer, you only need to ask one of them. All right, and so a lot of times I think that people approach sample size as saying that we need to talk to some set proportion of the population. So if there's 100 people in the population, maybe it's fine to talk to 50. But if there's 10,000 in the people in the population, now we need to talk to 5,000 people in our sample. That's not how sample size works. All right, so sample size is based on these three factors, and it has nothing to do with original population size. All right, and we'll see an example of this in just a minute. Okay, so on the previous slide, we saw that the variation in the population parameter that we expect, the amount of error that we're willing to tolerate in our estimation, and the confidence that we want in our estimation combine to affect the size of the sample we need. And a number can be put on all of these things, so we can estimate we can estimate numerically how much variance we expect to see in our population parameter. We can put a number on how much error we're willing to tolerate. We can put a number on how confident we want to be. And so because of that, we can use these numbers to come up with an estimate of the sample size that we need. All right, so remember, we're trying to answer this question: how many people do I need to talk to? All right, how many surveys do I need to send out in order to appropriately measure this thing that I'm interested in measuring, so that I can come up with a good estimate of what's true about this thing at the population level. All right, so before we get into the math that comes up on this PowerPoint slide, I want to point out one thing. This math is not going to be on the test. All right, the reason that we're going to go through this math here on this slide is because I want you guys to understand the logic behind the things on the previous slide. All right, and so for some of you guys, just seeing it and memorizing it, that's going to be good enough. For others of you whose brains work the way mine do, you have to actually see the math to figure out, how do these pieces go together. So we're going to talk about this on the next two slides, but just to reiterate, this math is not going to be on the test. All right, so it's just a learning tool. It's not something I'm going to test later, okay? All right, let's imagine that we have a very simple research question. All right, we want to estimate the GPA of Ole Miss undergraduates this year. All right, and hypothetically, yes, there's secondary data that we could use. If the university wanted to make students' records available to us, then we could calculate precisely undergrads' GPAs. But let's assume the university is not going to make those secondary records available to us, and so we have to collect some primary data. All right, and so we write up a survey in which we just ask students, what is your GPA? All right, and they write in a number of what their current GPA is on a scale from 0 to 4. All right, and so we randomly sample 25 students. Let's assume that this is a good, simple random sample that we talked about. We put all the students' names into a hat. We draw out 25 names. We contact those students. We ask them, what is your GPA? And we find that the mean GPA among those 25 students, the mean is 3.05. All right, so that squiggly X with the line over it is called X bar. That is the symbol for the mean within a sample. All right, and that sample mean that we've calculated has a standard deviation of 0.30. All right, we are not going to get deep into what standard deviation means, although we'll talk about logically what it means in a couple of lectures from now. But this is just a number that quantifies how different the answers that we saw were. All right, so a larger standard deviation means there was a much bigger range of scores that we saw, and a smaller standard deviation means that there was a much smaller range of scores. Everybody gave pretty much the same answer. All right, so in our sample of 25 students, we have this mean of 3.05 and a standard deviation within the sample of 0.30. All right, so remember, our goal when we are doing this research is that we are trying to estimate the GPA of Ole Miss undergrads. All right, and clearly there are more than 25 undergraduate students at the University of Mississippi, so we have to use this information that we got from our sample to make an inference about the population. All right, so based on what we learned from the sample, what do we think is true of the population? With these numbers that we have available to us, one thing that we can do is construct what's called a confidence interval. All right, and this is something that you guys should have learned about in Stat 1 or Stat 2. I'm going to walk you through it. All right, so we can estimate the mean for all undergraduate students. So we can estimate the population mean using this information that we got from our sample by constructing a 95 confidence interval that uses this formula. All right, and so because I don't have a chalkboard, all right, to flesh this out on, we're going to try handwritten notes put up on the screen, okay? All right, so here is that formula. To construct a 95% confidence interval, you are going to take the sample mean that you found, and you are going to add or subtract from that sample mean a margin of error. All right, and so the margin of error is all of that stuff on the right-hand side of the equation, 2 times the standard deviation divided by the square root of the sample size. All right, so in the second line, you can see that I've plugged in the numbers from our word problem. All right, our 95% confidence interval is going to be 3.05 plus or minus 2 times 0.3 divided by the square root of 25. All right, and as we start to do the math in this equation, we can see that this equation reduces down to 3.05 plus or minus 0.12. And in the notation of confidence intervals, it would look like this at the bottom in the parentheses. And the way that we would read this is we would say, based on the data from my study, I am 95% confident that the true population mean GPA of students at the University of Mississippi falls between 2.93 and 3.17. All right, so I have taken information from my sample, and I have used that information from my sample to come up with an estimate of what I think is true of the population. All right, so this is my best guess. Guess sounds unscientific, but this is my best estimate of what's true of the population. I know that what I measured in my sample, all right, this 3.05 up here, let me use a color that stands out more. This 3.05 up here is not exactly equal, all right, to what's true of the population, because I didn't talk to the whole population. I only talked to 25 students. And so we know that population parameter equals sample statistic plus or minus error. All right, so what we're doing here is we have our sample statistic and an estimate of our error. All right, and so we're saying what I think is true of the population is equal to what I learned from the sample plus or minus an estimate of how much error there is in my measurement. And so I think the true population parameter falls between 2.93 and 3.17. All right, and so to see the things that we were talking about on the previous screen, all right, these things that affect, sorry, let me get rid of all this, these things that affect the sample size that we need, this equation that I sort of poorly drew on the slides a second ago, the thing that we're interested in is estimating the population parameter, and in order to do that, we conduct a survey so that we can get information from a sample of people. And then to that, we add some estimate of how much error there was in our measurement. And that margin of error is composed of how confident we want to be in our estimation, how much variance, all right, so the standard deviation is a measure of variance, and our sample size. This 2 right here is stemming from the fact that we want to be 95% confident. If we wanted to be even more confident, this number would get larger, and if we wanted to be less confident, all right, then this number would get smaller. So if we were willing to be 68% confident, this 2 would be a smaller number, but most of the time people use 95% confidence, and so this 2 is in the equation for that reason. All right, so if we want this margin of error to get smaller, all right, so in our example, we had a margin of error of 0.12 GPA units, and that gave us a confidence interval of, I've already forgotten, 2.93 to 3.17. Let's say that we look at that and say, that's too wide of an interval, all right? I want to be more precise in my estimation. I need a smaller margin of error. All right, I want to be able to say, here's my best estimate of the population parameter, and I want that estimate to be more precise. All right, remember, we talked about 2 screens ago, if we want more precise estimation, then we have to increase our sample size. All right, and the reason why, our confidence is going to stay the same, so this 2 is going to stay the same. The variance in the sample is going to stay roughly the same. So in terms of decreasing this margin of error, the only thing that we have any control over is the sample size. And because the sample size is the denominator of this equation, all right, it's on the bottom of this fraction, if this number is larger, it will make the solution to this fraction smaller, all right? Dividing by a larger number gives you a smaller answer. And because we'll end up with a smaller answer, that means that our margin of error will be smaller. All right, so if we want a lower margin of error, we need a larger sample size. All right, and the useful part of knowing this is that it means that we can calculate for any specific margin of error that we want. All right, we can calculate a specific sample size that we need to get that margin of error. All right, so let's imagine that we want a margin of error of only 0.05 GPA units. All right, so we want to drop from our previous margin of error, which was 0.12 GPA units, and we want a more precise estimation now. All right, so we're going from 0.12 down to 0.05. How big does our sample need to be to accomplish that? All right, so rearranging this equation leads us to this one, all right, where we learn that the sample that we need is equal to 4 times the standard deviation squared divided by the margin of error that we want squared. All right, so over here we see 4 times that standard deviation of 0.30 from our word problem squared divided by the margin of error that we want squared. And the answer to this, all right, when you solve that equation, is a sample size of 144 people. All right, so what has happened here? In our original example, we sampled 25 students, and we ended up with a margin of error in our estimation of 0.12. If we want to decrease our margin of error, meaning that we have a more precise estimate of what's true of the population based on the answer we found in our sample, all right, we want to go from a margin of error of 0.12 down to a margin of error of 0.05, so that when we construct this confidence interval, it would look like 3.05 plus or minus 0.05. In order to do that, we have to increase our sample size, all right, from 25 to 144. All right, and the benefit that we get from doing that additional work, from finding those additional people, is that we get more precise estimation of what's true in the population. This example is done based on the thing that we're trying to calculate being a mean. Sometimes the thing that we're trying to calculate is a proportion, all right, not a mean. All right, we want to know what proportion of people would say yes, or what proportion of people would choose option A. And if we want to do that, the math is slightly different, and we will see that on the next screen. Okay, so the math for proportions, and remember, this is not going to be on the test, all right? This is just to help understand the logic of how sample size is tied to error. Let's imagine, new research question. You've been put in charge of a committee designed to improve the tailgating experience on campus. All right, and so your first step is you just have to figure out what proportion of students are tailgating on campus. Okay, so imagine you're on this committee and you're trying to improve the experience, and part of that is trying to make sure that there are enough bathrooms available, and there's enough walkways available, and there's enough food available, and enough everything. All right, the people need to have a positive tailgating experience. And one thing that's really going to affect all of that is how many students do you expect to be there? All right, and so we have to get a good estimate of what proportion of the population of students is actually going to show up, all right, to tailgate on campus before a home football game. All right, and so we could conduct a census, all right, but for all the reasons that we talked about, that's not going to happen. So let's imagine that you randomly sample 100 people, you survey them, and you ask them whether they tailgated prior to the last home game. All right, so you're trying to get an estimate of how many students are on campus, all right, for any given tailgating, any given home game. All right, and so let's say out of those 100 people, 76% of them answer yes. All right, so this is a nominal question, yes or no. Did you tailgate prior to the last game? We cannot calculate a mean of yes and no. All right, as we're going to learn in a couple lectures, the descriptive statistic that we report for nominal data is a proportion. What proportion circled yes, what proportion circled no. All right, and so here 76% of students answered yes. Just like on the previous screen, we can use this information to construct a confidence interval to estimate, based on the fact that 76% of my sample said yes, what proportion do I think would say yes if I could talk to the entire population. All right, the math for this is a little bit different just because we're dealing with proportions instead of means. All right, we are not going to get into all of the details of that. I just want you to know that the formula is going to look a little bit different because we're dealing with proportions instead of means. All right, and so here is the formula over here on this sheet of paper. All right, so we have a sample size of 100. P hat is the notation for the proportion who answered in the way that I'm interested in. All right, so 76% of people said yes, so P hat, my proportion of interest is 0.76. And if I'm going to use this sample information plus an estimate of my margin of error, all right, this part right here, that's how we're going to estimate margin of error for a proportion, then I'm going to construct a confidence interval of what I think is true at the population level. So I plug in my numbers, p hat 0.76 plus or minus 2, remember this is referring to being 95% confident, times the square root of p hat times 1 minus p hat, all right, 0.24, divided by the sample size. When that reduces down, my margin of error is 8.5%. And that means that my confidence interval is the proportion I saw in my sample plus or minus that margin of error. And the way that we read this again is to say I am 95% confident that the true proportion of students in the population that tailgated prior to the last home game is between 67.5% and 84.5% of students. Okay, so this is what I was able to do through this survey that, in this hypothetical example, we conducted a survey, we collected some information from the sample, we used that information from the sample to estimate something about the population. Now, on this committee, you might look at this and say, oh, an 8.5% margin of error, that's giving us a pretty wide confidence interval. All right, in terms of developing services for tailgating experiences, there's a big difference between 67.5% of the student body and roughly 85% of the student body. That would be thousands of students difference that we might expect. So let's say that we wanted to be 95% confident in our estimation with a margin of error of 5% or less. All right, so we're not satisfied with 8.5%. That's giving us too broad of a confidence interval. So we want a narrower, a more precise estimate, a narrower confidence interval. We want this smaller margin of error. As we learned on the previous screen, in order to accomplish that, we need, hopefully all of you at home are saying, a larger sample size. All right, so here's the calculation for this. This formula is going to come up on the next slide in case you guys want it. If you want a margin of error of 5%, the confidence interval formula rearranges itself to look like this. All right, so the sample size that we need is equal to 4 times p hat times 1 minus p hat divided by the margin of error that we want squared. All right, so here's that margin of error that we want, 0.05 squared. Here's our other numbers from the word problem entered in here. And when we do this math, this works out to, in order to estimate the population size, our sample statistic, p hat, needs to have been measured from 292 people. All right, so in our in our original example, we sampled 100 people. We got a margin of error of 8.5%. If we increased our sample size to 292 people, we would be able to reduce that margin of error to 5%. All right, so if we want less error, we need a larger sample size. Okay, the math is a little bit different. The outcome is the same. If you want more precision in your estimation, all right, holding confidence level and variation constant, then you need a larger sample size. The kind of interesting thing about the example with proportions is that, let me erase some of this. If we look at this formula, there's this interesting case of, let's imagine that we don't have any previous numbers. We don't know how many, we don't have a prior survey that tells us how many students tailgated on campus, and so we really have no idea how people are going to answer this question or any other question. Let's say I ask you, do you like chocolate or vanilla ice cream better? And I have no idea how students are going to answer. So my best guess at the outset is that half of students will say chocolate and half of students will say vanilla. All right, there's a 50% chance you say chocolate and a 50% chance you say vanilla. It's essentially a coin flip. All right, that's my best estimate in the absence of any other information about students' ice cream preferences. So if I want to estimate the proportion of students in the population who prefer chocolate to vanilla with a margin of error of 5%, then this p hat, my best guess, is 0.5. All right, times 1 minus 0.5, which is also 0.5. 0.5 times 0.5 is 0.25. 4 times 0.25 equals 1. And so that means that the sample size that I need is 1 divided by the margin of error that I want squared. All right, and I have to click to the next screen, but when we click to the next screen, we'll see what this means about margin of error and how it's tied to sample size. Okay, so as I was just saying, here is this equation for calculating the sample size that we need when we want any specific margin of error that we want when we're estimating a proportion for the population. And this reduces down, if we have no information about what proportion might say, chocolate or vanilla, this reduces down to 1 over margin of error squared. And the interesting thing about this is that if we just plug in different possible margins of error, we end up with this table right here. And the benefit of this table, I don't need you guys to memorize all of these numbers, but what I want you to see is that as sample size increases, margin of error decreases, but there is a diminishing marginal return here. All right, so going from 100 to 400 in the sample size cuts our margin of error in half. Okay, and that's great. We get a much more precise estimation by moving from 100 to 400 people. But as we start adding more and more people, the benefit that we're seeing in terms of a reduction in our margin of error gets smaller and smaller. All right, and so once we get up to about 1,000 or 2,000 people, we're seeing a very small reduction in margin of error. And if we wanted to drop this to 1%, we'd have to see, a much bigger jump in terms of sample size here. All right, and so because of this, one thing, if you guys start paying attention to polls, especially leading up to the election in November, if you start paying attention to polls that are posted online, you're almost always going to see that the poll was conducted with a sample size of roughly 1,000 people, and that they are reporting a margin of error of roughly 3%. All right, and so what that's going to look like is they're going to say there is a Democrat candidate and there is a Republican candidate, and the Democrat and the Republican are each getting some percent of the current people saying that they're going to vote for them. So they'll say, 45% of people in our sample said they were going to vote Democrat, 45% of people, 45% said they were going to vote Republican, and there's a 3% margin of error. And so what that means is that they think, based on their sample data, that between 42 and 48% of the population will vote Democrat, and between 42 and 48% of people will vote Republican. All right, and this is based on the fact that their poll was done with a sample size of roughly 1,000 people. This margin of error, and the fact that the margin of error decreases so little as sample size increases, is the reason why we just don't need massive sample sizes. All right, and so oftentimes teaching classes that are not this class, students will look at research and they'll say, well, the sample was only 2,000, U.S. residents, and there are 300 million people in the United States, so it's not good enough to only talk to 2,000 people. That's not true. All right, there is not much benefit statistically, all right, in terms of our ability to estimate what's true of the population. There is not much benefit to sampling more than 1,000 or 2,000 people. All right, and that's why almost all of the polls that you see online are going to have this magic number. It's going to be around 1,000, all right, 1,000, 1,100, 1,200, something like that. They're going to report this 3 to 3.5% margin of error. All right, and that's because you just don't get much more precise estimation once you get above 1,000 people. All right, so the cost of finding those additional participants is not worth it. All right, in terms of your ability to reach your goal better. All right, remember our goal is we get some information from our sample. We want to use that information from the sample to make an estimate of what's true of the population, and our ability to do that sort of peaks around 1,000 or 2,000 people. All right, and there's not much benefit to going above that. All right, so most of the time you're just not going to see people going above that in surveys of the population. All right, so on the last two screens, we were looking at a statistical approach to calculating sample size. All right, so remember, the question that we're trying to answer here is, how many people do I need to survey to get the information that I need to make an estimate of the of this parameter in the population? And we said that one way that we can approach this answer, all right, how many people do I need to get in my sample, is that we can look at what we're trying to estimate and figure out how precise of an estimate we need, and then use that information to calculate, this is the sample size I need to get the estimate precision that I want. There was math involved, okay? And so not everybody does that, all right? I understand, people look at the math and they say, oh, this is too complicated for me. All right, so there are other approaches to determining sample size, some better than others. In the previous slides, the math that we were doing was thinking about something called point estimates. So there was a single number that we were trying to estimate. The average GPA, that's one number. The proportion of students who are on campus at home games, that is a single number. However, the analyses that we're interested in doing are not always about estimating single numbers. And in fact, when you guys, when we get to data analysis in a couple of weeks, we're not really ever going to focus on point estimates, trying to estimate a single number for the population. Instead, we're going to be interested in comparative sort of analyses. Whose GPA is higher, the men's or the women's? All right, who is more likely to tailgate on campus, students or alumni? All right, so there are types of people, and we want to know if those types of people answered a question differently. When you were doing those kinds of analyses, you were using t-tests or chi-squared tests or analysis of variance, which is something we won't learn about, but it is relevant here. These tests usually require at least 15 people per type of person. All right, so if we wanted to compare the GPAs of men and women, we would need at least 15 men's data and at least 15 women's data in order to detect differences between those two groups. This 15 sample size per group is a bare minimum. All right, in terms of academic research, marketing academic research right now, the preference is to have 50 people per group. All right, so if we wanted to compare the GPAs of men and women, we would need a sample of 50 men and a sample of 50 women, and then compare those two groups. So this is going to be a problem when we do our data analysis, because for some of our analyses, like are certain races more or less likely to use these ADHD medications than other races, we will not have even 15, but certainly not 50 members of each of these races in our groups when we do these data analyses, and so that's going to limit our ability to draw conclusions from those analyses that we do, but we'll get there later. Another approach to determining sample size. This is one that's, it's unfortunate, but it's just what ends up happening because of reality. You have a budget for completing the research project. You've already spent some of that budget on writing the survey, on postage, for sending the survey out, for incentives, paying your staff, etc. All right, so you take the budget that you have available, all right, for collecting data in terms of how much money do you have to print the surveys, put them in envelopes, mail them to people's houses, incentivize them to take the survey, and divide that total budget by how much it will cost to recruit each subject, and that tells you how many people you can afford to sample. All right, so this is not based on any sort of logic. It's not based on statistical analysis. It's just get as many people as you can afford to get. All right, so it's not a great method, but it's a way that gets used sometimes. Another approach that you can take for figuring out what would be an appropriate sample size is to just look at how many subjects similar studies collected in the past. All right, so you guys read at least 10 papers, hopefully for your background research, and you may have noticed that in those papers, there tended to be relatively similar numbers of students who were surveyed as part of the study. And so you can just hope that someone else did some calculations about what an appropriate sample size was. Or at the very least, you can say, these other authors did a study with this sample size, and so we also did a study with a similar sample size, all right, because if it was good enough for them, then we'll say it's good enough for us. All right, so this is, again, not an ideal way to do it, but at least there's some justification here, all right, that someone else published a paper with this sample size, so it was, someone else has vetted that as being a decently done study, and so we're going to just imitate that and take the same sample size. All right, so as we've talked about sample size, one thing that has been sort of lurking in the background that we have not talked about yet is that all of these calculations refer to the number of surveys that we need to actually get back. All right, so if we do those statistical methods for calculating sample size, we calculate that we need 292 responses. Those are responses. We need 292 lines of data in our data set to result in a calculation with a margin of error that is tolerable to us. However, as we talked about earlier this semester, surveys have a high non-response rate. All right, so we know at the outset that a lot of people are not going to return surveys that we mail to them. So if we calculate that we need 292 responses, we can't send out just 292 surveys because over half of them probably will never come back to us. All right, so we need to calculate something called total sampling elements, which just takes into account the fact that people will fail to return our survey for a variety of reasons. And because of that, we need to pad our numbers in the beginning to account for the non-response rate that we can expect. All right, so total sampling elements refers to the number of population elements, the number of people in the population that need to be drawn and included in the initial sample pool in order to end up with the desired sample size. All right, and so people from that initial sample pool could fail to return the survey because we have incorrect contact information for them. All right, so we send a survey to an address that's not a real address or an email address that's not a real address. The people could end up being ineligible. All right, so when our sampling frame was created, they were eligible at that point, all right, but they are currently ineligible. They no longer meet our sampling criteria. People, of course, will flat out refuse to participate, and then there will be some people who can't be contacted, even after multiple tries. So we have correct contact information for them, but they never answer their phone, they never open letters, etc. All right, so they're not refusing to participate. All right, it's not like they saw the survey and said no. They just don't know the survey exists because we haven't been able to contact them. So what's happening here is essentially this down here is calculating the response rate that we expect. All right, and the way that we calculate that anticipated response rate is that we estimate what proportion of our sampling frame do we think we have bad contact information for? What proportion of our sampling frame do we think is ineligible? What proportion of our sampling frame do we think will flat out refuse to participate? What proportion do we think we're going to have no contact with? We plug those proportions into this equation. And let's say that the sum, the doing all of this math means that we anticipate getting a 50% response rate. That means that if we divide the sample size that we need, let's say it's 100, we've calculated we need 100 people to return our survey, and we divide that by 0.5, that would mean that initially we need to send out 200 surveys so that when 50% of them come back, we end up with 100 completed surveys. All right, so this idea of total sampling elements is just taking into account the fact that once we decide what our final sample size needs to be, we can't just send that number out. All right, we need to send out a probably much larger number so that once we account for non-response, we end up still with the number of data points that we need. This is relevant to you guys in a practical sense because if you need 10 people to take the survey and type your name in at the end of that survey, you are going to need to send the link to more than 10 people. All right, even if you send it to your 10 best friends and your 10 best friends all swear up and down that they completed the survey and wrote your name in, I hate to break it to you, at least one of them lied. All right, it happens every single semester. People come to me and say, but 10 people told me they took it. All that I have to go on is what the data set says. All right, I can't monitor what all of your friends are doing in their home. And so if 10 of your friends said that they did it, but your name only shows up 8 times, I have to go by that 8 that's in the data set. All right, so make sure that you are sending this survey link to more than 10 people to ensure that you get those 10 completed surveys that you need. Okay, let's take a break from math for an example. Okay, so as I have mentioned over the course of the whole semester, even if you guys leave this class, you never do any research in your job, that's okay. You are still always going to be consumers of other people's research. I mean, look at the news right now. All we are right now is consumers of other people's research, all right? Research about the coronavirus, research about people's responses to the coronavirus, right? And part of being a good, educated consumer of other people's research is being able to critically evaluate the quality of that research. Did they do a good job? Should I put any faith in, in what they found? And so we've already talked about one of the key things that you should be looking for is the quality of the questions that were asked. All right, did they include leading language? All right, did they include other, problematic sorts of things? And we talked about that when we were talking about survey design. But one thing that I've mentioned that we would get to eventually, and here we are, is that sampling is crucial, right? I can't overemphasize how much sampling decisions contribute to the nature of the responses that you get to a survey. And so one thing that you have to look at is, did they do a good job with their sampling? All right, did they get an appropriate random sample? Is the sample that they collected representative of the population that they are purporting to study? All right, so here's an example. When conducting a political poll, all right, and we are about to be inundated with political polls leading up to November, who should you be polling? All right, now if we were in class, I would stand in the front of the classroom, nobody would say anything for a full minute, then someone would tentatively raise their hand and say, voters? Yes. Most of the time these polls are looking at voters. Sometimes though they're looking at all people who are able to vote. All right, so they say my population of interest is all people who are able to vote. Sometimes though they say my population of interest is not all people who are able to vote, because not everyone who's able to vote is registered. And if you're not registered to vote, you can't vote. And so your opinion doesn't really matter in terms of voting outcomes, because if you don't vote, then your opinion's not heard. So we're only going to look at registered voters. Some people get an even narrower population than that, and they say, well, we're interested in talking to all registered voters who indicate they're likely to vote, all right, because these are the people whose answers are most likely to actually show up in the results of the final election. All right, so once we establish our population of interest, all right, either all possible voters, all registered voters, likely voters, the next question is, how should we draw a sample from that population? All right, how should we pick people out of that pot? All right, and so hopefully you said, to yourself after I asked that question, we need a random sample. All right, because we talked about how random samples necessarily result in representative samples because of the laws of probability. Some of you might have said we need a quota or a stratified sample. Remember, with the quota and stratified samples, you say there is a characteristic of the population that it is important to me to be perfectly representative on. And so I'm going to divide my population into those subgroups and then sample from those subgroups. All right, with a quota sample, that second stage of the sampling uses a convenience or non-random sample. And with a stratified sample, you divide your population into groups and then draw random samples from each of those groups. If you said quota or stratified, it's probably because oftentimes students tell me we need to make sure that our sample is reflecting the interests or reflecting the opinions of both Republicans and Democrats. All right, so we need to represent both of these groups in our polling. And the next question that I would have is, if we want to say, okay, we're gonna do a stratified random sample, we're gonna divide our population into Republicans and Democrats, and then we're gonna draw samples from those, what proportion of our final sample should be Republican and what proportion of our final sample should be Democrat? Now, I wish we were in class so bad, because somebody always raises their hand and says the final sample should be 50% Republican and 50% Democrat. All right, and on its face, this feels good. All right, there's two main political categories, Republican and Democrat, although independent is now the most popular way for people to register themselves. All right, but we have these two main political groups, the Republicans and the Democrats, and fairness dictates that their opinions should be represented equally in this sample. But remember, the goal of sampling is to create a representative sample. All right, so the people in the sample should exist in the sample in the same proportions that they exist in the population, which means fairness here is not an issue of 50-50. It's a question of what's happening at the population level and making sure that what's happening at the population level is also happening within our sample. All right, and so is our population 50% Republican and 50% Democrat? The answer is no. All right, we're not 50% Republican and 50% Democrat. Why does any of this matter? Here, this example is getting a little old, but sometimes big things happen in the news and it makes a good example for a while. All right, in 2011, all right, May of 2011, the AP reported a poll that they conducted of job approval. So remember, we've talked about this before. AP contacts people every week and says, do you think the president's doing a good job, yes or no? They reported that 60% of people said that President Obama was doing a good job, all right, in May of 2011. For some context, he ended his presidency with an average 57.2% approval. So this 60% isn't so high, you know, compared to this number. It was collected using a random sample. All right, so the AP used random digit dialing. So they have this simple random sampling technique, and they report in their their article that they posted online, their sampling information, all right, which is good. All right, remember I said that when studies are posted online, they should always tell you the sampling method, the questions, etc. So it's good that the AP reported this. But they said that their sample included 46% Democrats, 29% Republicans, 4% independents, and 20% of people said, I'm not sure. I don't know what party I belong to. All right. Do we think that this is a representative sample? All right. Do we think that these proportions adequately or accurately represent the population? Just, you know, ask yourself now, yes or no. Do I think this represents the population? We were watching Fox News, all right, my husband and I. Back then he wasn't my husband, whatever. We were still watching Fox News, and on Fox News we were watching the Bill O'Reilly show, and Dick Morris was on Bill O'Reilly's show. And for those of you guys who are not old enough to know this, Dick Morris previously frequently showed up on Fox News segments as the polling expert. All right, he was supposed to be the statistical consultant for Fox News. He was since fired because of not being great at being a statistical consultant, but anyway. Dick Morris and Bill O'Reilly were on Bill O'Reilly's show talking about how this sample reflects the AP's left bias, all right, what they were calling the AP's left bias, because the sample did not include 50% Republicans and 50% Democrats, all right? So what do we think about that? We talked about on the previous screen, all right, that we only want 50% Republicans and 50% Democrats if the population is 50% Republican and 50% Democrat. All right, and so in order to judge the quality of this argument, we need to know how well do these sample demographics reflect the population, right? Did they do a good job of drawing their sample? So I didn't know how well those demographics reflected the sample. I knew that the 50-50 argument was not a good argument because it was almost impossible for the country to be evenly split 50-50 with nobody identifying as anything else. But I wasn't, I didn't know for sure. All right, so because I'm me, when I heard this, I went online and I looked up actual voter registration at that moment in time. All right, and so that data came from this website, Pollster.com. At the time, Pollster.com was an independent website that just reported voter registration information. It has since been purchased by the Huffington Post, so I would no longer use it as an unbiased source of information. But at the time, all right, in May of 2011, this was an unbiased website. All right, and so in May of 2011, these were the actual population demographics. And over here, we have the sample demographics. All right, and remember, the accusation here is that the AP has a left bias because they sampled too many Democrats in their poll. But if we look over here at the actual population level demographics, 44% Democrat roughly, 30% Republican, 2.2 independent, 23.8 unaffiliated. To me, when I look at this comparison, this looks like the sample did a pretty good job, all right, of being representative here. This is the laws of probability working for us. If this is what the population looks like. All right, this is how many circles and how many triangles are in the population. Then if you randomly dip your hand into this population, you have a 43.7% chance of pulling out a Democrat. And as a result, that's why we get that proportion of Democrats in our sample. All right, same with Republican, independent, unaffiliated, etc. All right, so I think the AP poll was, doing a fine job. I think the 50-50 argument was unfounded here. All right, the reason why this was a topic that was being talked about is because the polls that week, all right, lots of different agencies do these approval rating polls, and the polls that week averaged 51%. All right, and they ranged from a low of 46% approval to a high of 60% approval. That's the AP poll. All right, and so the argument here was that the AP poll was so high, all right, because they had a left bias. What's actually happening here, all right, this range of numbers that we're seeing here, that's sampling error. All right, so this is reflecting the fact that if you take a sample, there is going to be some error in your estimation. All right, and so you are not going to get a number that is exactly equal to the population value. All right, our best guess of the population value is this average of all the polls here. You are going to get some number that varies around that population number. All right, so the AP poll was high because of margin of error, and this poll was low because of margin of error. All right, and so sampling and the specific people who end up in your sample, right, even if you use a simple random sample, if you took multiple simple random samples from the same population, each one of those samples would give you a different answer because you're talking to different people each time. All right, and so the act of sampling can dramatically affect survey results, and that's why we have to focus on what we can control, which is the quality of our sampling method. All right, and so when we have a high quality sampling method like simple random sampling using random digit dialing, you will tend to end up with a representative sample, and that gives you the best possible result that you could hope for. If these polls were done using non-random samples, right, so if they used convenient samples or something like that, then these numbers would vary even more dramatically, all right, from this 51%. Okay, another example of how sampling can affect survey results, and this time we're going to look at convenient samples versus random samples and seeing the differences here. 4-ish years ago, 4.5 years ago, when you guys were just babies who maybe didn't care anything at all about politics, there was a presidential debate. All right, and the presidential debate was between Donald Trump and Hillary Clinton. They were both vying for the presidency. Following that debate, a bunch of organizations posted polls on their website asking readers to, report who did they think won the first debate. And across organizations, that we might expect to go in favor of Donald Trump, like Fox News and Breitbart, but even in organizations that we might expect to go in favor of Hillary Clinton, like CNBC, we were seeing that in all of these polls, it was saying that Donald Trump won that first presidential debate, right? And so somebody made this infographic, and then, as he is wont to do, Donald Trump tweeted this infographic saying, Donald J. Trump wins first presidential debate. The next day, however, Politico and Morning Consult, all right, Morning Consult over here, this is a marketing research firm, all right, or a public polling firm, they're a consulting firm. They did a joint study using a stratified random sample of online polling panel participants selected to be representative of the registered electorate. This was their statement on their website about how about their sampling method, how they collected the data. And they reported that Hillary Clinton won, all right, and not by a small margin either. All right, and even, 12% of Trump supporters thought that Hillary Clinton won this. All right, and so there's this question of how can we have this poll over here finding such different results than all of these polls over here? All right, and part of what's happening here is that this poll was collected using a random sample, and these were all collected using convenient samples. All right, so the next, after this happened, this infographic over here, this thing right here, gets tweeted, and all kinds of news organizations pick up on it, right, and start reporting about the results of all of these online polls. Thankfully, Fox News, let me delete all these things. thankfully, Fox News released a memo the next day. Whoop, gotta erase that too. That said, as most of the publications themselves clearly state, referring to all of the online polls that were over here on the left-hand side, the sample obviously can't be representative of the electorate because they only reflect the views of those internet users who have chosen to participate. All right, this is a type of bias that we've talked about already in class, self-selection bias. We have a concern that the kind of people who chose to participate in the study, all right, who self-selected themselves into the sample, they weren't just randomly drawn and asked to participate, they picked themselves to participate, that those people may differ from people who chose not to participate. This is what we're worried about. Users who participate in such polls must have internet access, be online at the time of the poll, be fans of the website in question, and self-select to participate. All right, another problem. We know some campaigns encourage people to vote in online polls and flood the results, she wrote. These quickie click items do not meet our editorial standards. All right, she goes on to say, news networks and other organizations go to great effort and rigor to conduct scientific polls. They know quick vote items posted on the web are nonsense, not true measures of public opinion. Fox News policy is to focus on nonpartisan telephone polls that use live interviewers, random digit dialing sampling techniques, a methodology that enables everyone an equal chance of being interviewed. All right, remember, going back to the beginning of these slides, we said the key thing about these random samples is that everyone has a known and non-zero chance of being selected. All right, and that's this. Everyone has an equal chance of being interviewed. All right, and so this is just one more example. When you're looking at these results online, when somebody posts some dumb shit on Facebook, ask yourself, was this collected with any sort of scientific rigor? All right, did they do a good job asking the questions, drawing the sample, doing the data analysis before you decide to believe whatever gets posted online? All right, my little life goal is, even if I can't make you career marketing researchers, I can make you critical consumers of other people's research. All right, so this is my last slide. I know that this video has gone on forever. I promise that the other lecture slides won't take so long. The sampling slides normally go out over 2 days of class, so we are sort of in line with that 2 days of class thing. If you are binge watching all of the videos, then I will see you at the top of the next video about preparing our data for analysis. Otherwise, I will see you in a few days or maybe right before the final exam. All right, but I hope that you're coming to actually listen to these lectures. I hope that you are staying inside, all right, staying safe and eating some good snacks. All right, I'll see you guys later.